Hi, this video is the first step into reviewing numerous coordinate systems in 3 dimensions. The 3 most important coordinate systems that you're going to be using for a 3-dimensional space are number 1, Cartesian coordinates, number 2, cylindrical coordinates, and number 3, spherical coordinates. So the next few lectures are going to be just going through all these coordinate systems. You're probably really familiar with Cartesian coordinates, which would be your x, y, z axes. But maybe not so much with cylindrical or spherical coordinates. So we're going to start with Cartesian coordinates, and then we're going to have to switch quickly to polar coordinates, which you've learned before in your previous calculus courses. And cylindrical and spherical coordinates are going to be based off of polar coordinates, so it's essential that you understand polar coordinates before we even move on to those two. So later on, we're going to see how useful these coordinate systems can be depending on the situation we're given and what we're trying to calculate or solve. But first things first, every 3-dimensional coordinate system has to have axes that are orthogonal to each other or 90 degrees to each other. And in order to figure out where these axes are pointing and what they are, we're going to follow the left-hand thumb rule, which is represented by this. So using your left hand, you make a 3D axis that kind of looks like this. And you have 3 vectors with your 3 fingers. The middle finger always represents your first vector, your index finger, your second vector, and your thumb is going to be the third vector. So if I'm looking at the Cartesian coordinate system, usually it's x, y, z. So x is going to be my middle finger, then y is my second or my index finger, and we have z being the third vector, which is represented by the thumb. Let's start off with the left-hand thumb rule. So we have left-hand thumb rule. And we can draw a hand where you have your thumb, drawing the best thumb I can. There's your index finger, and then you have your middle finger, and then your other fingers are just like that. So you have vector 1 going this way. You have vector 2. With your index finger, and you have vector 3 going up. So if we were to simplify it onto an actual coordinate system, we would have something along these lines. We have an origin point. We have vector 1, vector 2, and vector 3. So in most cases, you're going to be seeing, for example, in the Cartesian coordinate system, x, y, and z represented in that order and configuration. So in this video, we want to focus on the Cartesian coordinate system. This is the system that you should be most familiar with because we're defining 3 unit vectors as x hat, y hat, and z hat. So, in other words, we have 3 unit vectors, x hat, y hat, and z hat, and they are arranged in this order. We have the x-axis, the y-axis, and the z-axis, and there's going to be unit vectors in each direction. So remember to use these three letters instead of the I, J, and K that mathematicians use. Why? Because we are applying math to physics and engineering, and in many cases, the variables I, J, and K could mean something else. So, especially K, we do want to be able to differentiate between different variables. So for E and M, we're going to use X, Y, and Z. So on the topic of directional unit vectors, keep in mind that you're only allowed to move in 3D space along any of these paths. So I can't just move in a path, for example, like this. That's not a path that I can take. I need to direct my paths taken either X in the X direction, then in the Y direction, and then possibly again in the Z direction in order to get to a specific point. So, in other words, it would make sense that we represent a three-dimensional vector A as a summation of all of the different paths that it takes. So, we can say that a vector A in 3D space can be represented by the path taken in each direction. So A would be equal to, as an example, we have AX, so that's the number of steps or unit steps that are taken in the X direction, then the number of steps taken in the Y direction, AY, and then the number of steps taken in the Z direction, AZ. So, as an aside, we'll write down AX, AY, AZ are the distances moved in the X, Y, and Z axis respectively. So when we're looking at three-dimensional space represented by three axes, we also note that there are three planes to consider. So I'm just going to say we must also recognize different planes. So if we draw our coordinate system again, then there is a plane here, and this is called the XY plane. And what's unique about this plane is that all the values of Z are going to be 0. Now let's take a look at the YZ plane. In this case, all the values of X are 0. And finally, we have our XZ plane. And just like you've guessed, the Y value is going to be 0. So this is where things get a little bit more complicated. For 3D objects, we don't just look at areas anymore, we look at volumes and surface areas. And that means we have three variables to consider because there's three axes. back in the 2D world, remember how we had terms like dx and dy for the differential elements? That basically meant tiny little steps taken in the x and y direction. So these are called differential elements, and they help us break up lengths into baby steps in each direction. So in the 3D world, we have 3 differential length elements to consider, dx, dy, dz, that can help us define arbitrary shapes. So I'm just going to start a new section called differential elements. So in the 2D world, we had dx and dy for the xy plane. So that meant if you were trying to integrate something or derive something, you would take a really tiny step. So maybe we could have like dx, and we could have dy. And this would be like a tiny chunk taken out of the shape that we're trying to figure out some sort of calculation for. Now in the 3D world, we need to define dx, dy, and dz. So if we have dx, let's say for some tiny volume over here, we have dx. Maybe we have dy like this. And then we might have dz like this. So that would mean we have all of these to consider. Creates a little volume. And that tiny little cube is, or that tiny little area or volume is going to be our differential volume element. So we can use tiny little pieces and tiny baby steps like this to be able to perform integrations to figure out either surface areas or volumes of the entire object that we're looking at. So continuing on with differential elements, there's different types of differential elements we have to be able to recognize. The first one is called a differential length element. So a differential length element is called dl and defined as dl is equal to some sort of tiny step taken in the x direction plus some sort of tiny step taken in the y direction and another baby step taken in the z direction. So it's very similar to how we represented the vector from before, but we now have baby steps taken in the x, y, and z directions to create a little tiny length element. You also have differential surface elements. So we already have differential elements dx, dy, dz. A differential surface element is when we multiply two of them together. So if we did do that, we would essentially get a differential area element, right? And because we're dealing with three-dimensional objects, we call these differential surface elements ds. So it is called ds and can be represented in one of three ways. Why? Because there's dx, dy, and dz. That means there's three different possibilities of multiplying them with each other. So we have, three ways. One, we have dx, dy. Two, we have dx, dz. And the third one would be dy, dz. So multiplying two differential elements together is going to give us some sort of area for one perspective of your 3D shape. So if we look at dx, dy as the differential surface element, it means that we are not moving in the z direction at all and simply looking at a small surface element on the xy plane. So going up to our drawing again and zooming in, we only care about dx, dy, which means we only care about this top surface area. Whereas if you had dx, dz, it would be dx times dz, so it would be the left and right sides that you could consider for surface area. So looking at dx, dy, we know that we are not moving in the z direction, but rather focusing on the xy plane. Although we haven't touched the cross product yet, it's useful here to define the surface element ds as a vector ds. So looking at dx, dy again, we call our surface element dsz. So we conveniently choose ds to be a vector and can define surface elements as follows. So we do this because the cross product of two vectors, the unit vectors x and y, is going to produce a vector that's orthogonal to both of them, which would be the z-axis. So it means that we would have three equations for our differential surface elements. We would have dsz equals to dx, dy. When we multiply the two vectors together, we know that its direction, the solution is going to be in the direction orthogonal to the two vectors. So it's the one vector that one variable that hasn't been involved in the multiplication process, which is z. We also have dsy, which would be dx, dz. And when we multiply it together, we know that it's going to be in the direction of y. Then we have dsx, which would be dy times dz. So if we cross dy and dz together, we're going to get an answer in the x direction. So we've covered differential length elements, then we've covered differential surface elements. The next logical one we should cover is the differential volume element. And we call this dv. So with dx, dy, and dz, we can easily calculate a differential volume element called dv. Looking at our diagram above, it's exactly what we've drawn on the Cartesian coordinate system. We have dx, dy, and dz, and it forms this tiny cube or tiny volume that we call a differential volume element. So when we're trying to figure out the volume for this differential volume element, it's simply just dx times dy times dz. So we have dv being equal to dx times dy times dz. And that wraps up our overview of the Cartesian coordinate system. The next few lectures are going to be based off of polar coordinates and are very crucial to understand. Please review them and ask questions if you are stuck.